So as HVAC systems age, we need to find a quick way to determine how to start switching over to heat pumps or in some cases dual fuel systems to help us decarbonize our housing stock and save people utility costs. While it's always a great idea to get a full green home inspection and energy audit, energy score on every home, sometimes we need to quickly yet accurately produce information on properly sized HVAC systems and determine if a home is ready for a heat pump. Now we can do that with existing utility data even before we get to the audit to get this information. So please join us here on this session today to learn how to do that. Before we get started, a huge thanks to one of our Platinum Plus sponsors, Rheem, with their ProTerra air source heat pump system. This is going to help us decarbonize and save energy on water usage, on our water bills for heating water, by taking heat out of the air at near 400% efficiency. They have 120-volt plug-and-play systems that can easily swap out gas, or they have all-in-one hybrid systems that have backup resistance heating for maximum hot water and comfort. These systems have leak detections, they have time of use programming. I've been using one now since 2018 to save energy, save carbon, and there is a limited tax credit that expires at the end of 2025 to get up to roughly $2,000 back in tax deductions, potentially if you consult with your tax advisor on these systems. So check them out over at greenhomeinstitute.org/REAMHPWH. All right, so again, welcome everyone to Let the Heating Bills Do the Math, Energy Load-Based Calculations. This course is brought to you by the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. Today, I will be your moderator. My name is Brett Little, and I am the education manager here. Like all of our courses, this course is approved for multiple continuing education units, including two of the 5 pillars of green in our certified green home professional designation. AIA Health, Welfare, and Safety may make it applicable to your state-based design or contractor license. Check out that 5-digit passive house code sent to you at the end as long as you've been appropriately logged in and attended the whole session, as well as check out that 5-digit code sent to you from our partners from Energy Smart Institute as an ICC preferred education partner, sponsoring the ICC CEUs for this session. So with that, I am excited to hand it off to our speaker today, Max. Max, welcome, and please take it away.
Awesome. All right. Like Brett said, we're talking about letting heating bills do the math, energy-based load calculations for HVAC systems. First, I just want to introduce myself a little bit. My name is Max Reichlin. I'm a professional engineer. I'm based in Washington State. I live outside of Seattle in a little town called Burien. So it's morning for me. Good morning. I think a lot of you folks, it's probably lunchtime. My background is various. I started actually in theater. I used to teach theater at Seattle Children's Theater, but then I decided I wanted to have a bigger impact on the world. And so I went back to school. I became a mechanical engineer. I went into industrial energy efficiency for a while, probably about 8 years. And then I got into product management. So now I work at Clean Power Research, which is a software company based in Bellevue, Washington. And right now I'm working specifically on Thermentor, which is an energy-based load calculator, which we'll talk about a little bit later. So I just want to jump in with kind of the elephant in the room, I guess. Like, why do load calculations matter? And there, people talk about lots of different reasons. I think the most salient one is comfort, and particularly humidity. If you have systems that are really oversized, you're more likely to get warm and cold spots in homes. And if you are in an area where there's a lot of humidity, then your risk of getting moisture imbalances goes up considerably if that unit is starting and stopping frequently. Another reason is longevity and reliability. Um, Again, that start and stop is not good for the equipment. Uh, when I was working in industrial systems, like we used to get actually, like it used to be in requirements for these companies that the motors had to not stop and start very often, right? They had to run continuously because they knew that they would have to do more maintenance if they were stopping and starting all the time. And finally, efficient performance. Um, I know that a lot of folks think of inverters, like we're starting to see a lot more inverter-driven systems. They can modulate their performance, and people think that that is a panacea, and it just covers up any errors you make in sizing. And the truth is that it does not. Most inverter systems cannot turn down all that far, like 30, 40% is like the minimum speed for a lot of them. And if you oversize too much, you really do end up at the minimum speed kind of all year. I've seen it, and it's a little silly. So you're paying a premium for what is functionally a single stage unit. So the kind of standard way to approach modeling these, trying to figure out what the loads are for a home, are what I call bottom-up methods. And they have some challenges. They're not wrong. It's not that doing a physics-based model and building up the home piece by piece is wrong, but it is time-consuming. If you're having to measure each section of the wall, you have to know how it's framed, you have to know what's inside of it. And particularly if it's not new, if it's not literally new construction and the drywall's not up, you kind of have to guess what's inside the walls a little bit. I know that my house was built in the 60s and it is not uniform. There's all kinds of weird gaps. I just actually recently found out that a random interior wall is open to the crawl space and was shooting cold air into my utility room unexpectedly. Um, and I don't think anyone doing a manual J on my house would have ever found that. The what ends up happening as a result of these kind of unknowns when you can't see or you don't have time to go see is that you assume there's less there, right? Someone looking at my house would probably say, well, it was built in the 60s. It probably doesn't have insulation. I'm just going to assume it doesn't. And assumptions like that tend to lead to oversizing, which leads to some of the challenges that we mentioned already. So what's an alternative? Well, we're here to talk about energy-based methods, right? I've also heard these called top-down methods, right? Like we're kind of looking at the home as a whole. We're not looking at the individual details. We're not building the home up piece by piece. The advantage here is that they're data-driven. We're already measuring how the home uses energy. It's on your utility bill. We already know what the weather is like. Like there's many sources for weather data. So we can take a kind of consistent data set and then make draw conclusions about how the home performs depending on the weather. And unlike a bottom-up method where you're not looking at everything, it takes into account those hidden details, right? It doesn't tell you that they're there. Like no one would be able to tell me using a utility-based method that I have a weird hole in my wall. But it will take it into account because my home is using more energy because of that, right? So this gives us a good block load calculation. If you need room by room calculations, then you're going to have to move to some other, you're going to have to add on some additional work. But if you're thinking about the whole home and what the whole home needs, this is a really good place to start. So what specifically do we need? I kind of talked about it a little bit to do this. We need monthly temperature data, we need monthly home energy data, and we need some information about the equipment efficiency. Now, when I say monthly, sometimes people are like, well, wait, wouldn't you rather have hourly? Wouldn't you rather have 15-minute data? Wouldn't you rather have 5-minute data? And the answer is surprisingly no. For analyses like this, what we find is that if you get too granular, it gets really noisy. you start to see all of the kind of weird effects of people coming and going from the house and opening and closing a particular window. Um, you know, the sun goes behind a cloud for a few minutes. And then also the thermal mass of the home matters more, right? All those little kind of transient effects create a tremendous amount of noise when you're looking at just a little bit of data. It's a little bit like the waves versus the tides. The waves are chaotic. You can't really predict exactly what's going on with the waves, but you can predict the tides. And what we want to do is zoom out a little bit so that we can see the tides of how your home uses energy. Um, so what we found is monthly works fine, and that's what we're going to talk about today. We've also found that weekly is really good. So if you are an overachiever and you want to do it with weekly data, I think that's a great idea. We'll talk a little bit more about equipment efficiency in a minute, but it is important to know what is currently being used in the home and how efficient it is, so you can kind of translate from that utility load to what I call the comfort load. So why does this work? Sometimes people are confused that this is even possible. Heat is energy, right? Energy can transform into different things. We do it all the time. And we have to replace heat as it leaks out, right? Your home is constantly leaking. You can't avoid it. Physics requires it. How much it leaks depends, right? And so your HVAC system is going to be replacing that heat. I guess I should say real quick, all of these analogies, I'm going to kind of couch this in terms of heating, but it applies to cooling too. The mechanisms for moving heat around and cooling are a little bit more confusing, so I'm just not going to talk about them, but the concepts apply. So if your heat is leaking out of your home in the winter, and you're adding the same amount of heat back, you're going to be keeping the level the same. It's like the bucket, right? If you add too much, then the bucket's going to overflow. If you add less than what's leaking out, the bucket's going to empty. And that's how it works with your furnace. Your furnace is constantly adding just the right amount of energy back into your home to keep the temperature the same. And it does that because that is a thermostat, right? Like that's what that control is for. And this is kind of the secret sauce here, right? Like the energy that your furnace is using is the same as the energy that's leaking out. There are some like caveats here, and we can talk about those caveats a little bit. But broadly, that is why this works. Another caveat is what I mentioned earlier, which is the equipment efficiency. And this one is an important one, so I want to mention it. If you're burning fuel, if you're burning oil, if you're burning gas, some of the energy is leaving through the exhaust, right? You don't want those combustion products in your home, so you have to get rid of some of it. And depending on how old your furnace is, it'll have different levels of efficiency. And I'm sure a lot of you folks are familiar with that. Same thing applies to heat pumps and air conditioners. We don't call it efficiency, we call it a coefficient of performance, but the idea is the same. It's moving a certain amount of heat with respect to how much energy it is. And estimating the efficiency there is a little bit more subtle. But the key detail here that I want to remember is that if we know roughly what the efficiency is, then we can predict what the comfort load is as that equipment is running. Another question that I get about this is, what if we never hit the design condition, right? Like maybe the last year was mild. It only got to 30 and our design condition is 20. How do I know it's going to work? Well, the answer is a little mathy. I'm not going to dwell on the math part here too much, but heat moves mostly because of temperature. This is a kind of simplified heat transfer equation where Q net is kind of the flow in and out of your home, right? This first term here with the temperature outside and the temperature inside over R, this is like the thermal resistance of your home to changing temperature. And this represents the conduction and convection of heat moving in and out of your home. And this is actually usually the biggest part of this whole equation. There is a load associated with solar, the sun just kind of shining in. And there are also internal loads, right? Like you're cooking, you are a person and you generate heat. Your dog generates heat. And those loads matter. But for our purposes, we're kind of just going to ignore them. They are, when we zoom out to that tidal level, they kind of fall away. They're roughly constant in an area for a home. And so we're gonna mostly look at this first part. But let's make it even a little simpler. Let's try to make it plain English here. We care about the comfort heat, and we can kind of anticipate what it is. We know what it is if we know how much energy the home is using and what the efficiency of the equipment is. We know the outside temperature, we know the inside temperature, but then there's this thermal resistance here, this little magic term, and we don't know what that is, right? But if we can take all 12 of those utility bills over the past year, and we can look at how the different temperatures responded to the different outside temperatures responded to the different inside temperatures, and how much energy the home required, we can actually get a picture of what this magic number is. And it turns out that by and large, this number is constant for a home because this thermal resistance is more or less constant. You're not changing your home's insulation every day. It does change a little in those transient ways, like if you're opening windows and things, but it doesn't change kind of at that tidal level. So once we can figure out what that magic number is, we can just plop in the design temperature into this equation. We know the magic, we know the design temp, we know what temperature we want it inside the home, and that gives us our design loads. Now the way we actually literally are going to do the math is slightly different than this, but that's the idea. Because the home behaves these kind of fundamental physics-based behaviors, right? It's following what physics says. It's following the heat equation. We can take data and then predict a condition that we didn't actually see. So next, I'm going to do a little walkthrough of a way to do this, a utility-based kind of calculation. I did this in Excel, and I think we're going to be able to provide the spreadsheet after the webinar if you're interested in it. I'm just doing heating loads just to kind of keep it simple. It says regression. It says temperature regression. And I don't know if you've heard that word before. Maybe you haven't, maybe you haven't. Try to remember that regression is just drawing a line through a bunch of points. Excel's going to do the work for us. Like, you don't need to know too much about what regression is. So, step one, we're going to gather data. We're going to gather utility data, 12 months of utility data, preferably. You want to get a good heating season and cooling if you're doing cooling. This is an example bill from Puget Sound Energy. And you can see it's got average therms per day. You want to make sure that you're using the right, obviously the right utility data for whatever, however the home is actually heated. And if there's multiple sources, like you might need to add them together, and we can talk about that a little bit. Watch out for these average therms per day or CCFs. You need to do some conversions to make sure things are in the right units for you. Then you're going to need some kind of weather data. A common way to do this is using heating degree and cooling degree days. It's kind of a classic strategy. Degreedays.net is a great free source for that. I have no connection with that organization, but you can just go in and say what your weather station is and what kind of data you want. You do have to pick a base temperature. It recommends 65, and this is a pretty good default. for what we're doing. Kind of the idea here is that some of those other loads that I was talking about that I said were tidal, like the sun, like that kind of drags the point where your home starts needing heat down a little bit. So even if you keep your home at 70 degrees, you might not actually start heating it until it's 65 outside. And so that base temperature kind of takes that into account. And so it's a pretty good way to approach this um, if you're trying to do it kind of manually in Excel. So you're going to want to get those degree days that match up with your utility data, and you're going to need to know your design conditions. There's a great tool, this ASHRAE Meteo site. I have no idea who runs it, but I love it. I visit it constantly because it just like has all the ASHRAE climatic conditions, and it's just really easy to click on it and figure out which weather station is going to be best. So once you have those, then we're going to do we're going to start doing some Excel work. I'll try to go through this a little quicker because it's not super fun watching someone talk about Excel. First thing we need to do is normalize our data. Our months are not the same length. It's unfortunate. Some of them are 29. 29, look at that. You know, it changes. It changes from year to year just to make it even worse, right? And so then we're going to divide our total heating degree days by the number of days. So we get kind of a per day value, and that kind of makes everything kind of in the same scale. And that will help us make a clear model that's not weird and noisy. Next thing we're going to do is we're going to convert our utility data and also normalize it. So in this example, we've got utility data in therms. We're going to convert it to BTUs. I like converting things to BTUs because that's kind of the standard energy for the industry that we use for HVAC loads, right? The other advantage of this is if you have electric loads and gas loads, say, or oil loads that you want to evaluate, you might want to add them together, and you can kind of just convert them and then throw them together as BTUs. And so that kind of makes everything kind of one-to-one. And then you got to normalize it. Same thing, except for I like to normalize this by the hours because then our units are already in BTUs per hour, which again is industry standard. Like this is how equipment is sized in the United States. And so it's easy to use these numbers. This is already going to feel familiar to you if you're used to working with heating and cooling loads. The next step is we want to kind of calculate that comfort load I talked about. You want to take out that utility load or adjust. There are base loads. Sometimes there are more and sometimes there are less. If you're talking about gas, for example, if the home has a gas water heater, there'll definitely be like an annual base load that kind of runs all the time. Maybe the cooking loads, there might be a dryer, all those things. And so we want to pull those out. And we're going to assume for our purposes that those are constant through the year. So we're going to look just at the lowest value in the set, and we're going to subtract it from all of these numbers. So all the 1000s here, this is synthetic data, to be honest. It's not, real data is not going to look this pretty. These all go to 0 because we're subtracting out that base load. The next thing we need to do is we need to take into account that equipment efficiency because not all of that energy is going into the home's comfort, right? We know that 20% of it in this case, because it's an 80% efficient furnace, is just going out the stack, going out the flue. So we take that out, and that gives us how our comfort load is changing throughout the year. And from there, we can plot and do our regression. We can take our heating degree days per day and our comfort load. Heating degree days per day is on the x-axis, comfort load on the y, and we will get a line most of the time that looks something like this. This is just a scatter plot. It's pretty straightforward. You can add a trend line in Excel just by right-clicking on the graph, but you can also, if you want to get fancy, there are formulas. There's a few different ways that you can find the slope and intercept and the R-squared values in Excel if you want to do it that way. But what we want to know is what does this linear function look like? How does the home's energy per day change? How does that comfort load change depending on the heating degree days? And remember, I was talking about the magic earlier, right? Like this is the magic. We're going to do the math a little differently. We're going to take the slope, we're going to multiply it by our design heating degree days, which I've calculated here as 53. I forgot what the design load is. Is the design, yeah, the design temp for this, I did this for Spokane, Washington. So the design temp is 12 degrees there. And so taking into account our base temperature of 65, that gives us 53 heating degree days for Spokane. And when we do that math, we multiply 53 by that slope, we add the intercept, that gives us our design load for this particular home. This imaginary, admittedly imaginary home, but the idea stands, right? And you can see how this kind of all lines up, right? And this works for most homes. There are a few, things you have to look out for, right? I've seen data sometimes where it gets there's like a weird periodic thing. It'll kind of jump up and down, and you gotta try to assess what's going on there. Is it a real effect or is it just like an artifact in the data? You can use that R-squared value to give you a clue, right? The R-squared value for this is 99. It's excellent because it's fake. You're probably going to get lower than that. And if it's using the R-squared is good. I personally, I like to use my eyes. I'm a person and I can read a graph, and if it looks reasonable to me, that's like the best sanity check for me. If I see if I see that some of these data points are like way outside of the line, I start asking questions like, what's going on here? One of them might be vacations, right? Sometimes people go on vacation for a whole month, especially if they like go to Europe or have family in another country, right? Like there's going to be there might be some kind of weird deviations. Another thing that you might want to consider doing is making the periods more precise to your data. Your billing, your utility data might be monthly, but more likely it's going to fit some billing period, and it might be close to the month, but it might be like halfway through the month. And so you might need to go to like a daily weather data and kind of like group the data together differently to make the energy use match well with the weather data. And you'll get better results that way.
Max, maybe you're going
Yeah,
to
what's
bring
up?
this up, but I'd assume for those who are using electric vehicles, who have solar,
Oh, yes.
they're going to have to be hopefully managing that all pretty well to, somehow account for that, right? I mean, can you speak to that a little bit?
Yeah, of course. Thank you for asking. Yeah, yeah. Those can both be very tricky. So, EVs are a large electric load. And if you're looking at a home that has an electric furnace, electric heat source, you do need to know if some of those big electric loads exist. Pools can also be kind of tricky. Like if you've got a big pool pump that you're only running in the summer and you turn it off in the winter, that can create some kind of weird variation. Um, and so you're going to want to, talk to the homeowner, especially if you're seeing things that don't make sense. Generally speaking, these loads are going to look lower. Like if you're a person that does heating loads at all with manual J based tools, for example, you're going to see these and you're going to be like, oh, that's low. Because homes, I mean, generally speaking, people are oversizing stuff, right? And so they're not used to seeing these numbers. Even so, like you have to know kind of, oh, there's a pool in the back. What are you doing with your pool pump? Like, let's talk about that. Because if your load is jumping up in the summer, partly because there's a pool pump running, like you want to take that into account. If you have an EV, it's probably fine uh, in an analysis like this if they've had it for a long time. But if they bought it 3 months ago or 6 months ago, there might be a big jump in their use. And so you're going to want to take a look at that as well. And hopefully you can get some data about the energy the car is using. Um, when it comes to solar, the utility bill is usually not going to be helpful because, especially if they're like close to zero energy use, if they have a significant solar system that's covering more than 80% of their energy, you're really going to want to get the data from the solar system. And there's a lot of apps today um, that make that a little easier. And like you said, Brett, like if people are um, you know, thoughtful, capable homeowners, they'll probably know how to get that data. It's not a guarantee. So you just have to do your best. Um, you definitely don't want to try to do a utility bill analysis with a home that has solar and ignore the solar because you'll get a really strange result. You'll get like close to no load because, the home's energy use might show up as negative on the utility bill sometimes.
Yeah. So really, I mean, this spreadsheet approach almost sort of ideally the homes that are to even without solar electric cars have those plug load monitoring systems, right? And they're telling you, and they don't, of course, those plug load monitoring systems don't work on gas appliances, right? They
Right.
don't.
Yes.
So that's one. So again, just a bonus for electrification. We can get more information, more data that we can't get. You can't get a plug load analysis on your gas water heater, other than maybe it firing up to remove the deadly gases that it puts in your house. But other than that, but yeah, having again just information, right? If people can get information, if you can work with people to get data, their electric car, their solar, their plug loads, um, that sounds like it's key. So if you go back to that other slide you were on, the other question was just to clarify again, what is R squared again? Can you clarify that?
Oh, sure. So R squared is a statistical metric that we use to like determine how closely the line matches the data, right? Um, like how far away from this trend line are these data points? So if like this is very good, right? The R squared is 99.99. It can go up to 1. 1 is a perfect match. In this case, it's 0.9891, right? And this is synthetic data. There's some little wobbliness here because like clearly I included some numbers. There's like 0 zeros here. And so it doesn't perfectly exactly match, but it's very, very close. Um, for uh, if there's no relationship between uh, the data and a line, right? Like it's not actually following a line, the R squared will be very low. It would be like zero point 0.2 or something, or maybe 0.4. Um, and again, this kind of goes back to like using your eyes. Like we're people and you want to see a line. If it looks like a line, you're probably good. If it does not look like a line, that's when you need to start kind of asking more questions. Like, why doesn't it look like a line? Are there particular data points that are out? Should I throw some of them out? Don't throw them out for no reason, just because they don't fit. Um, but if it turns out that they were on vacation, maybe you should exclude that one, and you'll probably get a better result. Um, yeah. R squared is one of these. All of these metrics, these kind of statistical metrics, have weaknesses and strengths. In this particular application, R squared is a fine way to kind of like think about whether the regression is doing the right thing. If you find yourself with something that doesn't look like a line and it's only 0.5 R squared, take another look. Um, the spreadsheet's great. I want to show you Thermentor. Thermentor is available online for free. Um, it is not the only option in the universe. There are a lot of ways that you can solve um, uh, doing these kind of utility load calculations. And doing it by a spreadsheet is fun. Believe me, I love Excel, but sometimes it's faster, especially if you want to kind of do it routinely for your job. There are online tools that can make it a little easier. Um, so we're going to walk through Thermentor. The QR code on the screen is a link to the demo, and I will also share my screen and walk through it. Brett, is there anything else we should talk about before we jump into the demo?
Yeah, and I was just gonna say I will throw that link into the chat here so you all can access it as we're going if you can't get the QR code. But yeah, so and maybe these are also questions. I think these are all going to be great questions here for, either approach, right? The sort of hand approach or the digital approach. Um, some of the assumptions that are being made. So yeah, why don't we just if you're pulling your screen up right now, go ahead and jump into it and we'll bring these up to see if they're not answered. So
Sure. All right, I have to reshare my screen so we can see Thermentor. There we go. Can you see that, Brett?
yes.
Super. So this is Thermentor.com, and this is where we have our current version of the tool, which is public facing. It's free to use. Um, let's get into it. So the idea here for Thermentor is it's kind of like broad strokes, same thing. We're looking at how energy use will help us learn about how the home behaves, right? It'll draw the line for us, so we don't have to build an Excel sheet. It's got some little warnings, just like we were talking about EVs, pool pumps, those things. So if when people are walking through this, they're kind of alerted to those questions. It's also intended to be kind of anonymous, right? This is not meant to sell you anything. It's just trying to help you get useful information. I'm going to put in Spokane because that's what my other example was. We are adding, we've added most of the states at this point. I think the outlier is Alaska. And that's because our weather data source, which is another product of CPR, is called Solar Anywhere. It doesn't have Alaska. It doesn't have enough of Alaska yet. They're working on it. I hear they're going to add it soon. So we've got design conditions based on that. But if you want to use different design conditions, you can. And I didn't really talk about this, but one of the things that I like about this energy-based approach is that if you want to be conservative, it gives you a way to be conservative kind of thoughtfully and in a data-based way, and not in a, well, let's just add 20% more, right? Um, if the homeowner that you're working with says 12 degrees is fine, but I'm really scared of polar vortices, how are we going to handle those? Then you can work with them and you can pick a design temperature that makes sense for that project and is allowed in the code requirements for your area, right? But you can but then you can change that design temp and you'll still know what the loads are going to be at that alternate design temp. You do have to be thoughtful about your municipal requirements there, so be
Yeah, and
careful
I
about that.
Max, I'm thinking like for like some of the green programs and just a good idea, people run their um climate risk analysis, right? And it kind of gives you this risk, whichever tool you're using as to, in this case, cold waves, as you mentioned, or what of course, and what I'm going to be experiencing here today, a heat wave.
Yeah,
And like, okay, like assuming these things might happen more often, get worse and someone wants to design for that, 10 years down the road, you
right.
can kind of do that here, right?
Yeah, yeah, exactly. I mean, that's kind of what we're thinking about here with these design temps. If you're like, I know that the extreme condition is -20, Like you can see what your loads are going to be at -20. And then you can take that into account as you're designing the system. Now, how you meet the load at that point is a kind of a question you're going to have to work through, right? Like you may or may not be able to use a heat pump if you really want to be perfectly comfortable at -20. Um, uh, and so that's something you're gonna have to think about. And but the point stands that like this gives you a data-driven way to look at what that condition is, right? And so it's kind of a starting point that is data-based, and that's what I like about it. Um, we think about design conditions as like um, they have like they occupy a kind of weird space sometimes where they seem like they're the most important thing. But if you add a bunch of stuff that's not data based around them, then they kind of don't matter anymore. Um, this gives you a way to like make the design conditions matter, and you can select them in a way that makes sense for your project. I'm not going to change them today. I'm just going to leave it at 12. And we're going to keep going. So uh, you can pick the heat source for your home. Right now we've got gas, electric furnace, a baseboard, portable heater, which we're assuming is electric. We're adding delivered fuels soon, maybe next week. we're actively debugging it, so we'll be adding that soon. If you're picking something that is using a fossil fuel, you're going to need to give us the efficiency of that equipment, approximately. We also want to know about how your thermostat is kept. And this is fine to give us like an average if you're using setbacks. How are you using it right now? And how do you want it to be? One of the things that we encounter a lot in the energy efficiency world, I imagine a lot of you have seen this, like homeowners might say that they want to save money on their electric bill, right? But then when they have an efficiency project done, they actually want to be more comfortable more than they want a lower electric bill. And so this is kind of a way to kind of nudge them about that. If they say, oh, I'm keeping my furnace at 66, but I want it to be at 70, we're going to predict different bill changes. I didn't say this, but like in addition to load calculations, Thermentor does a couple other things that are helpful for projects, and we can talk through that. When it comes to cooling, we're not actually analyzing cooling signals right now. We're going to start doing that pretty soon. That's also in the slug of work that the delivered fuels include. I'm just going to leave that off for right now. But again, the concepts are very similar. And we have similar questions around like where people keep their thermostats. We ask about the square footage of the home and how many floors it has. And this, for a lot of people, makes them think of those bottom-up calculations. They think this is like crucial to calculating the loads. But thinking back to what I just showed you in Excel, the square footage of the home was not in that spreadsheet. It is not important for that calculation. This is just to help us evaluate the kind of overall efficiency of the home. And so we ask about it because of some calculations we do, but we don't need it for the loads. For putting your energy into Thermentor, you can put in the actual energy, which is definitely the kind of the most accurate way to do it. If you want to get like the best possible result, use the actual energy from those heating bills. You can, however, sometimes people really have no idea how to get their energy use, and getting their total cost for their bills is easier. This is especially good, for people that have like gas or are on tiered electric rates where it's pretty flat and does not vary over the day. If you're on a time of use rate, this requires us to make a few more assumptions, and it kind of like widens the error bars. So you want to take that into account if you're using the total cost. I'm going to use this typical home, which is for demo purposes. We don't encourage people to use this for an actual home because for all of the reasons I said at the beginning, people do not always know where their home is in terms of how insulated it is. So we're going to calculate the heating and cooling loads from that. We've just put in the energy data. Thermentor knows where we are because we told it our location. We're going back to CPR's other product, Solar Anywhere. We're collecting that weather data, and then we're doing that regression. We're also calculating what we call the effective R value. This is that resistance value that we had to calculate, right? Remember that? We didn't really see it in the spreadsheet, but here we have run the numbers. And this is just like the R value for your insulation, but instead of being just the insulation in the wall or just the insulation in the attic, it's kind of the whole home together. And it's not arbitrarily from 1 to 10. This is just how much we've shown. These numbers can go as high as 20. A very efficient home will be 17, 18, 19, 20. Occasionally we get results that are higher than 20, but those are often errors, like something has gone wrong in the data collection. What we've also found is that homes that are below 6 are good targets for weatherization. They're not using energy very efficiently. Homes that are above a 6 are going to be more kind of like electrification might be an appropriate next step if you're thinking about kind of like the best value for the homeowner. We've got our version of the loads chart. And so this has both cooling and heating loads on it. And so you can see how again, this is synthetic, so it lines up beautifully. But you can see the design temperature there and the design loads for summer and for winter. And then we also write them out down here below so you can see those. We have a database of incentives and rebates. We expanded the coverage for weather data much more rapidly than our incentive coverage. So this probably doesn't have a lot for most of the country. You know, the West Coast is particularly filled in when it comes to incentives and rebates. But we hope to add better coverage for this. We wanted to make sure that the loads were available for people kind of first, and then we're kind of like going through in waves to get the other aspects covered completely. And this is really just meant to be like a summary to give you an idea about what might be available to you. The last step is the bill impact. One of our other products is called Watt Plan, and it is backed by a rates database and rate engine. So we already collect electric rates, and we already built an engine for utilities around the country. We don't have everything, but we have a lot of rates. And this allows us to do billing calculations. We can take the kind of current state, we can see what those bills look like based on the energy data we got, and then we can do a proposed state where we can say, okay, well, we're going to take out that furnace, we're going to put in this heat pump, and we're going to see how those bills change. Now, right now, we're assuming that they're not completely turning off their gas. So normally, almost, I can't even think of one that doesn't, you know, the vast majority of utilities have kind of like a fixed fee per month. And so that is always in all of the bills that we're showing here. At some point, I'd like to add, you know, the ability to say like, oh, I'm actually shutting off my gas. I'm capping my gas line, or I'm pulling out my my boiler. It's gone, so that I'm no longer using those things, and so those fixed costs go away. But you can see here that we have the monthly kind of cost changes. We modeled this without AC, so it adds some cost associated with cooling. And you can see that for a home in Spokane, Washington, it's pretty even for switching to a heat pump, for going from gas to a heat pump. The total monthly bill impact is down $6, which is, you know, functionally zero, right? Like, because it won't be exactly this. So, but we can also add a backup source. If you want to look at keeping your natural gas as a backup, or you want to switch to an electric backup, you can do that. I like doing this because I think it highlights really well the danger of setting your switchover temperature too high and having strip heat. So you can see here now, I have a switchover temperature of 30 degrees, which is well above the design temp for this area. It doesn't actually get that cold most of the year, but you can see how, since we have a backup, our auxiliary system is strip heat, it's electric. Uh, our bill in January suddenly spikes hundreds of dollars. Like this is a really important, this is a really important detail, and people sometimes set this too high because they're afraid of homeowners being uncomfortable. Um, and what we should really be worried about is this. Now, if you have dual fuel, the risks are lower, right? Because natural gas is cheaper per unit of energy, and so having a high changeover just means you're going to be burning more natural gas. And if decarbonization is a particular goal for you or your client, then obviously you're going to want to like minimize that switchover temperature. Um, when I've talked to manufacturers recently, like they, generally recommend don't put one. Just let the unit turn off, uh, uh, or like have a setup where if it's unable to maintain temperature in the home, then it comes on, that kind of thing. Uh, the last thing, we don't need to. We're running out of time here. I don't want to keep everyone. We do generate a report, so this is just like a free, lightweight experience. It's meant to be anonymous, so you don't have to put in any contact information. The consequence of that, of course, is that nothing is saved. So your only real way to save things is by getting a report. So you can download a report from Thermentor that has kind of the same details that I just went through, so that you can kind of preserve it for posterity. I'm going to switch back to my deck, and we're going to wrap this up. So that is essentially what I wanted to tell you about today. Please, if you have questions in the coming days, please feel free to reach out to me. My email's there, mreiklin@cleanpower.com. I threw the links for degree days and for Thermentor in there. And I think that Brett will be following up with GHI members for some other stuff. Yeah. I guess that's it. I guess I'm ready for questions. Any thoughts, Brett?
Yeah, absolutely. Let's dive into those questions. And as those questions are coming in, just a quick reminder that yes, this session is being recorded. You can access it within a week on our YouTube channel there, or you can go there right now, hit subscribe, ring the notification bell, and you'll receive an instant update when it is available. For those of you watching this in the future, not right now, but on demand, take your quiz with an 80% passing rate and you will receive your continuing ed. For those of you here live, make sure to review our webinar policy and our webinar CEU policy to receive the information. But you can check your spam for certs@gutenbergcerts.com and you should receive it. And again, as those questions are coming in, we're going to get to them. But just a huge thanks to our board of directors, our volunteers, our executive director, Jose Reyna, our almost 500 members. We're trying to get there by the end of the year. So if you haven't yet, click subscribe. We're trying to reach that goal for our 25th year anniversary. And a huge thanks to all of our sponsors who are making products to help with decarbonization, green building certification strategies like REAM for decarbonizing water heaters, SERV for intelligent HVAC ventilation, Tamarack, Timber HP, and all of them who support our work. So yeah, Max, there were some clarifications that were coming in here. And one of them I think was just about, you know, asking the question about air leakage. Do we need to know air leakage? And so, obviously there's the first approach. You talked about the spreadsheet. There's this approach. Where do air leakage assumptions kind of come into that?
Yeah, that's a great question. So air leakage kind of has two major impacts, right? Like one of them is your just on the temperature, on your sensible load, right? So if the leakage is primarily a concern that it's introducing cold or hot air when you don't want it, then this kind of energy-based approach should take that into account kind of
Mm.
natively. Uh, it's a little more complicated if the concern is about um, humidity, right? Now, if you've got an air conditioning system that is capable of removing the humidity in the home, but maybe it's not sized right, or maybe it's not as efficient as you want, or maybe you want to switch from an AC to a heat pump, right? Um, then in principle, it's
Mm.
the leakage is kind of included as well, right? It's like part of that load that it's taking care of. But maybe it only takes care of moisture when it's on, but it's cycling, and
Mm.
so like it actually feels kind of humid in the house because every 10 minutes it turns off again. Um, so uh, knowing what the leakage is, I think is especially important for humidity. Um, and when it comes to like Thermentor, for example, like we're going to take an approach that there's kind of a middle ground that we need to take for homes that don't have AC, where we're concerned about the potential for a humidity load. We're going to do a kind of by hand, more like a bottom up calculation to kind of estimate what that latent load looks like. Um, so you can kind of take that into account when you're figuring out what those cooling loads are.
Yeah, no, I'm glad you brought up humidity because yeah, that I mean,
It's a big one.
obviously when people are switching their HVAC system, it's becoming more alarming these days about switching to heat pumps and not fully addressing humidity. So it sounds like perhaps you've got some thoughts for that too then. Are you looking at building anything out that might look at it a little bit more in depth?
Yeah, yeah, we definitely are. And it's, another thing that's important to consider, right, is and this is particularly true kind of in the north part of the country,
Mhm.
northeast, where you're getting humidity and it's cold, right?
Right.
And so you really need to be cautious about like if your cooling loads are twice what your or if your heating loads are twice what your cooling loads are, and there's a humidity, load as well, which is what you get in the Northeast. You really need to be kind of cautious about that sizing and make sure that you are taking that into account. Um, I've heard of some kind of novel people doing kind of novel things where they're like installing two compressors, right? Where they have one that's really intended for the cooling loads and one that's intended for the heating loads. Um,
Yeah.
Doing the system design is obviously more complex in those circumstances.
Yeah. Um, so the other question he has here, uh, following up further review of this program, um, and wondering like would like to see a heat pump option on the existing heating and cooling in the
Yeah,
event that it exists. So right now
yeah.
it looks like you just have electric resistance. Now, obviously, the intent here is trying to help someone find a heat pump. So I assume someone's trying to switch to a better heat pump or a more right-sized heat pump. So how do they deal with that right now?
Yeah, yeah, that's a good question. So right now we just don't support existing heat pumps at the moment. It's not that we can't, we just haven't gotten to it yet. There's a lot of
Right.
work we have to do. Um, uh, we are kind of, like you said, we're like a little bit focused on kind of trying to like drive adoption right now. We do want it to be like kind of a full service tool that can help with any system. So we do want to add heat pumps, existing heat pumps. Um, we just haven't done it yet. There's no reason in principle that we can't do it. We do need to, um, like I talked about, we need to know about the equipment efficiency. And so we'll need to ask some questions or make some assumptions about what the efficiency of the existing heat pump is. The nice thing about furnaces and boilers and electric furnaces is that efficiency question is very simple. It's a little more complicated with heat pumps and air conditioners. Um, but the data that I've seen kind of indicate that like uh,
Mm.
uh, it, it, it's not too
Mhm.
difficult to draw assumptions from those like the SEER values that
Yeah.
work pretty well.
Yeah. The other question, and I'm going to kind of add a little bit in, but is it wise to consider refinements for number one, anticipated change in HDD based on climate. So I think we talked about that one already. But number two, this really gets more into, so the specific question is for anticipated increased cold season thermostat settings as
Mm,
home occupants age. But I'll add more to that. I'll say, as whatever the issue may be, right? It could be anything that affects somebody and they feel cold or they feel hot. Um, where does that kind of come into play? Or does that really then get into like, okay, I've got this information. Now you're talking about the contractor kind of coming in and saying, let's get, your personal information. Like, how does that work in?
yeah, yeah, that's a good question. So, I would consider that when you're doing these load calculations, because like how, um, let's see, I wonder if it'd be good to use a picture, right? Like this line is going to move around depending
And I
on
can't see your
where.
screen if you want to
Oh, that's
something.
right. I'm
Go,
not sharing.
yeah, go ahead and share if you want.
Let me share again. Yeah. Can you see that now?
Yep.
Okay. So this line, the line, um, is going to move depending on those thermostat settings. It doesn't necessarily change slope, but it will slide from side to side depending on how conservative or aggressive people are about their thermostat and things like that, right? And so um, I think it's an important thing to consider. If you are working with a client that is older and you know that they're going to want to maybe not right now, but maybe in a few years they're going to want to like push up that temperature a little bit, like it's wise to kind of like take that into account. And for like this heating degree day analysis, what you can do to reflect that is like just kind of bump up that base temperature. We use 65 for this. That's a good number for most homes. If um, if they need it to be warmer, just like use 70. And that will probably take that into account. It's kind of squinty. It's not very precise, right? But that at least gives you some kind of notion of that. I would talk to them about where they're keeping their thermostat because your heating system is going to turn on, 5 to 8 degrees lower than wherever your thermostat is set. When outside air temperature, when the outside air temperature is lower. So just, you're gonna have to talk to them about that to select that base temperature that makes sense. For Thermentor and tools, maybe tools like it that are kind of doing this automatically. In Thermentor, we have what's called we call that number the balance point, that point where the system turns on. It's a little confusing because there's multiple ways that people use the word balance point. So don't get caught on that. It's the point where the heating system turns on. Um, and we calculate that based on the data. Like we can kind of like we watch for when that line kind of picks up and we say, okay, that's the balance point for this home. And what we can do is we can shuffle that balance point around by based on the predictions about people's needs in the future. So in Thermentor, you said like I keep it at 67, but I'm anticipating that I'm going to be cold in the future. I
Yeah.
want it at 72. And then we'll actually just slide the line over and it'll increase the loads. And
Yeah.
so it takes that into account.
Yeah. Do you foresee a future of automatic utility integration and reporting? And so thinking of this in a couple different ways. Number one is, you get sometimes, depending on how savvy your electric company is, it's usually electric more than gas these days, but you kind of get this report. Here's how efficient you are compared to your neighbors. You could do this, you could do that. And then I think about the on the home resale side, the home disclosure policies that are springing up across the
Oh,
country. You have to in some way report utility usage as compared to square footage, as compared to many things. So what I'm getting at is, do you foresee a future where you automatically just have this automation? Because someone asked a question about AI too, and someone else
mm-hmm.
asked a question about API with your system. So I was just expanding on those questions and thinking, is there like an API with the utility companies or with some agency where you're just getting these are just getting cranked out, right? We just drop in an address, poof, there it is. Where are we at with that?
Yeah, yeah. Yeah, that's a great question. So there's a few different answers and it's complicated, of course.
Yeah.
Um, so Clean power research works with utilities kind of actually as our main business. I didn't talk about clean power at all, but like like principally we sell products to utilities.
Mhm.
Um, so we have a lot of experience with the energy industry, with utilities in particular. There is a kind of double-edged, well, there's a couple like layers here. One is that a lot of utilities are kind of like, yes, they're getting more connected. They are not well connected yet. Um, and when it comes to your your energy data,
Yeah.
uh, a combination of, oh, that's in a hard to get database because it's maybe 20 years old. That plus, oh, now your energy data is PII and we can't give it out on your behalf. So there has to be this like kind of careful, like people are just terrified of revealing personally identifying information that's PII. Um, and so, and it's not that they shouldn't be, but like the this the combination of old technology and security policy makes it really hard to get that data. There
Right.
are a world where you just drop in your address and it just automatically gets it from utility is
Mhm.
not near.
Okay.
um, but we
We
are
can
working.
always dream.
Oh yeah, we can all stream. We are working on, and another kind of layer to this is there might be multiple utilities involved, right? Like if you
Uh,
have a gas
right. Yeah, we have that
furnace
here.
and
Yeah.
AC, right? Like there might be two utilities that we care about.
Yeah.
So what we're working on is uh, like we're actively working on ways that we can kind of ingest a
Mhm.
bill or a picture of a bill and
Mhm.
kind of get the data from it um,
Mhm.
as easily as possible. So people can just
Yeah.
like, okay, here's my gas bill, here's my electric bill, go figure it out,
Yeah.
and we can do that.
Yeah.
And that's driven a lot by the advancements in LLMs and stuff.
And I think
Um,
this, specific other question was, the API availability. So if
yeah,
another agency's like, I like this, I want to API my energy audit program to it. Is that something?
yeah. Actually, I'm glad you asked because that is something that we're actually looking at more seriously now. So we
Yeah.
we have the user interface is very simple. Uh,
Mhm.
and I know that some organizations and some companies would rather like kind of like handle that themselves,
Yeah.
the interface part, or they
Yeah.
want to integrate it with another experience. So
Yeah.
yes, we are talking about adding a web API that's kind of
Mm.
publicly facing so that people can
Mm.
use it.
Yeah.
Um, yeah, yeah.
And then,
And if you're more curious about that, please feel free to email me and we
yeah.
can talk.
And then, so I might have missed what to do about boilers. So the specific question here is, can someone just chuck in a gas furnace until the boiler is available?
Yeah, I think you can probably get away with that if you have a notion of how efficient the boiler is. Yeah,
Oh,
that should be fine.
okay.
They're not so dramatically different that it's not gonna work at all.
Yeah. And then the other question is the question is about if someone wants to model ground source heat pumps, but then they ask kind of clarifying further, is it best to separate the heat and cool subsystems due to the climate humidity issue? So I guess maybe it's a specific question, or how do we do ground source in this? So,
Yeah, we're not really. So when there's a couple ways to think about this. So step one is like load calculations, right? Like that's kind of like the heart of it. The load
yeah.
calculations are not going to be different because you're doing geothermal, right?
All right.
Um, So that's great. That's easy. When it comes to doing the billing estimations, and like kind of more into the system design, that those questions get more complex. And we're not, um, I am not familiar enough with geothermal heat pumps to like speak uh, with any kind of confidence about like those system designs. Um,
Would it be fair to say that typically geothermal has less worry, especially on the heating side, right, of meeting the design temps? So would you almost say that perhaps you'd be oversized, right? If you were just looking at it apples to apples.
I mean, let's see. So, like, the real advantage that you get from geothermal, right, is that you're no longer
Yeah.
um, the available energy for you to use is coming
Mm.
from the earth and not from the air, right?
Right.
And so, like, your advantage is that it's really stable.
Yeah.
Um, and so it doesn't
Mm.
matter as much how the temperature is changing outside if you're using a geothermal system.
Mm.
Um, and actually, if there, if you had an, well, no, it would still work. Yeah. Uh, yeah. So, uh, yeah. What was I going to say? I distracted myself. Um, yeah. So that, I mean, that's like your key advantage for a geothermal system, right? But it still needs to meet the same loads because, like, fundamentally, it kind of doesn't matter what's behind the vent as far as this analysis is concerned, right? Like, we need to know the loads of the home. And it doesn't matter if it's a geothermal heat pump or an air source heat pump or like a magic genie. Uh, it's still going to have to meet the loads that the home requires.
Mm. Right. Right. Um, and I think their specific question is, well, then, dealing with humidity
Right.
for specific to geo. I guess that just sounds very niched, kind of.
Yeah, I think
Yeah.
that yeah, we'd have to like dig into like the design details and
Yeah.
like what like equipment options exist,
Right.
right?
Yeah.
That's not something I have very much expertise with.
Yeah. Um, and then just talking about kind of next steps with some of the resources available. So one was kind of going back to just the general Excel document approach. We'll send that out, but is that something that, for example, gets also listed on your site as an alternative? And someone's increasingly wondering, will CDD be added to that eventually?
Uh, I had not considered that I would persist the Excel document,
Right.
but I suppose we could put it in there for your members for fun.
Yeah. Yeah.
um, uh, yeah, yeah. I don't expect that I'm gonna I'll have to think about that. I don't know. I hadn't considered like putting the Excel document just on the Thermentor website. That's not crazy. Maybe we could do that. That's kind of
Yeah.
fun. Um, just as like a resource for people. Yeah.
Yeah.
Yeah, I'll think about that. That's a good question.
Yeah. And so they were saying, and so I was thinking if it's on there and there's future iterations, someone mentioning that the CDD is missing from it, or if it was being updated to it, I guess.
Yeah, it just didn't I didn't put in the CDD. I wanted to kind of keep our conversation today a little bit constrained
Yeah.
because it could
Yeah.
I didn't want it to spiral.
Okay. Um, and you were mentioning some hiccups with Alaska, but is this available across the United States?
Yeah, yes, I'm going to cautiously say yes.
Yeah.
It's got almost every state in there. We kind
Yeah.
of did areas we didn't kind of like uniformly go across the country. And so we were
Yeah.
adding states over months. And so I think that 49 states are in there right now.
Yeah.
Um, but there might be, oh, is New Jersey not in there? Okay, we'll add New Jersey. Sorry about that. It may just be that we're waiting for a release to get the like last
Yeah.
couple in there.
Yeah.
And that's why it's not there. Yeah.
Yeah. Now we have someone came in from Canada and posted a great link to another resource there. And we have
Oh
people,
yeah.
someone came in from India. We have people all over the world. And typically what we do in those cases, when people are looking at our energy software, we're trying to match a climate address in the United States with wherever they're out on the planet. Is that
Mhm.
something that could work for our non-US folks here?
Yeah, I mean certainly parts of it,
Yeah. I know there's
right?
also construction types outside of the US. They're like more concrete, right? They're more
Hmm.
different
Yeah, I mean
construction types. So, yeah.
again, the kind of like great thing about utility loads is that we don't
True.
care how
Yes.
it's constructed as
Right.
long
You have to
as
keep remembering that. Yeah,
yeah, yeah, yeah.
yeah,
I know it's like
yeah.
it doesn't matter. But yeah. So in terms of doing the like load calculations, is actually we could in principle do most of the planet. Like if we have the like location, if we have the lat
Right.
longe of the house, like we could figure out um, what those what the weather is like, and if you give us the energy use, then we could do it. You know, likewise, a tool like I don't actually know. I haven't looked at international tools, but I'm sure there are weather data sources available, you know, kind of internationally. So you could do that if you wanted to kind of do it manually. Um,
Yeah. And
uh,
our education chair, Debbie, posted an international HDD
there
link
you go.
from ASHRAE. So
Perfect. Yeah.
we'll share that out. So yeah.
Oh, it's in there too. Oh, that man, I love that website. The other thing I was going to say though is the billing calculation, like Thermentor, like in
Yeah.
terms of load calculations, that's a good idea, and you could do it you could do it manually today, probably using like a tool like that ASHRAE site. In Thermentor, like we do the billing calculations, and we do not have any billing. We don't have any rates. We might have a few Canadian rates. Canada is something that we might cover at some point because I know there's interest there. Um,
Yeah.
but not right now. Yeah.
Yeah. All right, Max. Well, we are at our time. And so I guess just real quick, can you remind everyone where they can go to access these resources or contact you for more information?
Yeah, of course. Yeah. I just like I said, like please feel free to email me, mreichlen@cleanpower.com. You can also just go into thermentor.com. That's our tool, but there's also a contact us there if you have questions about what we talked about today. Um, that's great. I didn't put it on there. I'm on LinkedIn. Please feel free to, you know, connect with me on LinkedIn if you want to chat. Happy to talk about interested people, people that are excited about this topic. I
Yeah.
think it's fun. It's not every day that I get to be this nerdy, so I enjoy it.
Well, I appreciate that. And yeah, well, thanks to Max Reichlin and Thermentor for coming on out and taking your time to do this. I really appreciate it and the conversation. And thank you all for joining us. And we'll be on with our next event, same time, same place next week. So take care, be well, all. Thank you.
Thanks for having me.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.